Back at it with the pink hat. I still dig the pink hat. I love your name, by the way. UBMAE student. Just nice. Just generic. Welcome, everybody. It's Wednesday. Part 2 for the days. How are you guys feeling today? We'll give it like another minute or so. Have you guys tried the Discord yet? I think I need to play with the settings. I think on Discord it makes everybody a temporary user. And so I guess it's easier for you to get booted for some reason. I don't know if you guys are having that problem. Good afternoon to the big white whale. Can't wait to learn. Very nice. I can't wait to learn either. We're gonna finish up this pinned airfoil today. Where's everybody? We only have 26 people, it looks like. Do you guys have another class before this? there's 51 on your screen. Okay, maybe my number's just behind. All right, let's get started. Oh wait, they gone. Let's get started. So I want to do like a... I gotta turn this music down. 4:51 is before this, but there's no other lectures this week for that class. Okay, no problem. Just curious. Okay, so a little bit of a recap. We're doing flight dynamics, right? And the first problem we're looking at is this 1 degree of freedom pinned airfoil, and the pin we are talking about is this one up at the front leading edge. So this whole airfoil can rotate about that pin, and yeah, there is another pin at the back that this elevator can rotate about. You know, it can get into different configurations, but we're looking at the rotation about this front pin. So we have the weight of the airfoil itself, and that has a perpendicular distance from the pin, so that creates a moment. And we also have the lift, and that has a perpendicular distance from this pin P, that creates a moment. And we were also considering the moment that's caused by this elevator at the back, and depending on the angle that it's at, that'll change the moment that that element produces. Okay, so we went through Newton's second law, which is basically if you take the moment of inertia about that pin joint P, the moment of inertia times the angular acceleration should be equal to the sum of moments. So we just added those up. And what we found is that this results in a nonlinear equation. But, and this is why we brought up this example. In this class, we're going to do a lot of linearization. So you're going to have a nonlinear equation. We're going to simplify it to a linear equation. And that opens up a lot of analysis that we're familiar with from a class like 340. And we'll get into those solutions today, actually. So when you're doing a linearization, it's popular to linearize about an equilibrium point. So we solved for, if we have the elevator at the back fixed at some angle, what is going to be the equilibrium angle of attack? So I called that alpha naught. So we went through some of this. Well, in general, like for, say, an arbitrary elevator angle of, say, 5 degrees, you have this nonlinear equation that you'd have to solve for alpha. That's one of the homework problems. Have you solved that on the homework yet? So you're going to have to use like fsolve or something like that in MATLAB. And so you're going to wrestle with this on the first homework. Now, but for now in the class, we're dissecting a simpler case where if the elevator angle is just set equal to 0, then it's much easier to solve for the equilibrium angle of attack. And we saw that this equilibrium angle of attack, it's kind of embedded mathematically in the lift force, because lift is a function of the angle of attack, and it varies with angle of attack like this. It goes up linearly with angle of attack until you get to the stall point, and then the lift dramatically drops off. We all know stall is not a good thing. You lose lift, you get more drag. So here we go. So we can also write out lift in terms of the coefficient of lift. Let's look at this. Okay, and basically, if you have the coefficient of lift, you can solve for the equilibrium angle of attack in this like mathematical expression. So once you solve for an equilibrium point, we linearize the dynamics about that equilibrium point. Now, I think that's what we're getting into here. And when you do linearization, what you're solving for are the perturbation dynamics. And those are dynamics that are valid in a small neighborhood of the equilibrium point. The equilibrium angle of attack is when the moments about the pin sum to 0. Yes. Yeah. That's a good way to think of it. The moments sum to 0, and for that reason, there's no angular acceleration, and the airfoil is just fixed in that position. So when we solve for the perturbation dynamics, we're saying, okay, let's assume we are close to that equilibrium where it's fixed. And then if we were to bump the airfoil a little bit, what is it going to do? Is it going to like go unstable and just flip around? Or is it just going to like oscillate about that equilibrium point? So the perturbation dynamics there in terms of perturbation variables, you can recognize them with that delta out in front. And the thing to remember about perturbation variables is that they're small. How small? Well, when we get into this Taylor series expansion, so this was our nonlinear equation, but we did a Taylor series representation where we said, okay, this right-hand side function, whatever this nonlinear stuff is, we just called it f. And using Taylor series, you can rewrite f as the function evaluated at the equilibrium conditions plus some partial derivative terms and so on and so forth. Well, the point is, if these perturbation variables are small enough, then these higher order terms that just go on and on and on and on and on, we can basically ignore them. And all you're left with is a linear equation, which I think we got to down here. This is the general form of it, but this equation of motion, it's linear in terms of the perturbation variables. Like in the original nonlinear equation, we had like cosine of alpha, and that's a nonlinear expression of alpha. Now it's just this constant times delta alpha. So it's linear. And, okay, you have to do the work of calculating these partial derivatives. We did that. And yeah, here they are. You evaluate those partial derivatives at the equilibrium point. And we found, I think this is where we stopped. I think this is where we ended up. So for that pinned airfoil, for an arbitrary elevator position, this will be the perturbation dynamics about whatever equilibrium that creates. But we know that there's a simpler equilibrium condition if you just set the elevator angle equal to 0. So that's where we're going to start today. We're going to assume that this is 0, and that's going to make our linear equation even more simple. I know it doesn't look super simple right there, but it's gonna get a little simpler. Okay, so we're almost at the end of this handout. And then when we finish this today, we're going to move on to another handout, and we're going to blast through that. So hopefully you have those in front of you. How can the linearization not go to 0 if the perturbation is supposed to go to 0 in the higher order Taylor series? How can the linearization itself not go to 0 if the perturbation is supposed to go to 0? Well, I don't know. Are you talking about the perturbation variables, like these deltas? Let's go up here. Let's go to the Taylor series. Well, these perturbation variables, they don't go to 0. They are just small. And how small is the question? Small enough that if you have a term like this, that we're going to say it's not going to be 0, but it's going to be so small that it's like, let's neglect it. And so it's not perfect because we're assuming that these terms go to 0, but they really don't. And that's why I think if you pay careful attention, let's go down here. Now, when I cut out the higher order terms, I changed the equality to this squiggly equality, which just means approximate. So because those terms that weren't really 0, we made them 0. This is now an approximate relationship. And the approximation gets better the closer you are to the equilibrium. I hope that answers your question, Dilly. Okay. So if the equilibrium elevator angle is 0, this condition for the lift happens. Now, if you were to take this and plug it in up here for this lift coefficient, so we're going to plug in L1 over L2 times the weight. Well, you're going to have the L2 terms cancel, and you're going to have L1 times the weight minus L1 times the weight. And this whole term multiplying the sign is going to go to 0. What are L1 and L2 geometrically? Good question. Yeah, we gotta. So, just giving you guys a second before I scroll up to show you that. I think L1 is the distance between the pin joint and the weight vector. And L2 was the distance between the pin joint and the center of pressure where the lift is applied. So I'll scroll up real quick, just show you that. Oh, buddy. Yeah. So L1 is the distance between this pin joint P and the CG. And then L2, distance between the pin joint and the center of pressure. I know that drawing is getting really busy. Well, when I post these, it'll be very clean. So those will go up after class. Oh, wow. Let's keep going. Sorry, skipping around there. Okay, so a bunch of stuff is going to go to 0, and this is going to simplify the equation to, let's write it out. Let's write it out. Minus L2, the derivative of the lift, and let's put function of alpha in there, and then we're going to evaluate this partial derivative at the whatever equilibrium angle of attack it happens to be, times delta alpha minus this moment coefficient times the perturbation in that elevator angle. And that's it. So by just changing the equilibrium elevator angle, we've made this equation a little bit happier. Yo, what's up? Welcome. Okay. And then we're gonna break this down a little bit more, because we know that the lift is related to this lift coefficient. So all right. So this is the lift. So if we differentiate this with respect to alpha, we're going to get 1/2 rho, that relative wind velocity speed squared, times the planeform area. And then we have this, the derivative of the coefficient of lift with respect to alpha. And we're just assuming this is a constant for now. And okay, that's multiplying alpha. And we evaluate the whole thing at alpha naught. Okay. So basically we're just expanding the lift expression. We're writing it in terms of the coefficient of lift. Oh yeah, in this class we're going to save our writing a little bit. When we have the partials, we're going to tend to express that partial as just another subscript. So the partial derivative of is the previous filled out note posted? I can't find it. It's not yet. I'm going to post it after I finish this handout. So we're going to finish this one within the next like 10 or 15 minutes. And then I'll post this filled out one after class. And then we're going to start the next one. So I'll post them online after we finish them in class. So the partial of something with respect to alpha, we abbreviate that with the coefficient of lift, and then you just add a sub alpha, and that indicates taking partial with respect to alpha. Oh, sorry. I don't mean to skip around like that. Okay. So now we're going to write our full linearized equation of motion. We're just expanding out this coefficient of lift. Why is the derivative of the lift coefficient with respect to the angle of attack taken in the formula for lift? Why is the derivative of the lift coefficient with respect to the angle of attack taken in the formula for lift? So you're saying, like, why is this in the formula for lift? Okay. So let's break this down. So lift, this is good for me too. It's a force, right? And then the coefficient of lift is non-dimensional. And so lift you write like this. And this coefficient of lift changes with alpha. So this is lift. And then here we have coefficient of lift. Now we know that if we take lift and plot it as a function of angle of attack, you tend to get something like this, right? So going back to this formula, the only thing in this formula that varies, that's a function of alpha, is this coefficient of lift. Now we see that, so tuck that away. We see that the lift varies linearly with alpha, basically, until you get to stall, right? So that means that lift is basically some constant times alpha, right? And this constant is it's the slope. Well, I guess it doesn't intersect at 0 here, so you should have like another constant. So I'm guessing when I write this, we're actually assuming that the coefficient of lift has some offset too. But the point is, the lift is some constant, it's some slope times alpha. So we break down this coefficient of lift into, oh, sorry, I didn't realize you had already taken the derivative because the lift function on the left wasn't differentiated as well. Well, that's the point. Like, this is not differentiated. And yet, this partial still shows up here. So but why do we expand the coefficient of lift into DCLD alpha times alpha? So I guess that's what I'm trying to say. Like, this coefficient of lift, just like you could say the lift is some constant times alpha, I'm saying the coefficient of lift is a constant times alpha, but we know the constant is the slope. And so the slope would be the partial of the coefficient of lift with respect to alpha times alpha. So yeah, this right here, I'm sorry, I'm probably explaining this in the most roundabout way, but this term right here is the coefficient of lift. Yeah, it's just an approximation to simplify the math. It breaks down around stall. Thank you, miracle. You're a miracle. Okay. So I'm rewriting our perturbation equation. Rho u infinity squared s, that's the area, L2, and then instead of the lift itself, we're writing this in terms of the coefficient of lift. I want to make this clean. So, but it's the coefficient of lift. It's the partial with respect to alpha, evaluated at the equilibrium angle of attack, times the cosine. We divide this by the moment of inertia about the pin. And then this is equal to this moment coefficient for the elevator, and then times the delta. Is that an S or a delta before L2? That's an S. This wasn't an S. And this is the, once again, the plane form area. And that's like if you're on the ground looking at a plane in the sky, and if it's like right above you, it's like that underside view of the wing. So I guess if this is like the plane and it's got its two wings on either side, like that area. Okay, these are our perturbation dynamics about the equilibrium point. And what we're going to do, because writing all of these symbols is a little bit of a drag, we're going to replace that big coefficient here with, we're just going to call it a K. So it's K times delta alpha. And for now, we're going to ignore, we're even going to ignore the perturbations in the elevator on the right-hand side. So I'm just going to make this homogeneous, set it equal to 0. And once again, this K parameter, it's the same thing up above. Goes right there. Whew! It took some time to get to this point. And there's a lot going on here. Okay, but I know we have arrived. Why isn't the right-hand side of that equation not over... Oh, very good point, Dakota. Thank you. Okay, so what Dakota's saying is, over here, we have this moment coefficient times delta, but it should be divided by this moment of inertia about the pen. Thank you very much, Dakota. Because, well, I don't want to keep scrolling up and down and giving you a seizure, but we had that moment coefficient multiplying with our angular acceleration, and we divided it through everywhere. So we should have, I should have divided it over there. Dilly says it all comes back. Springs. Yeah, exactly. Basically, we have a second order equation here. And if you remember how this works, and we're going to get more into this on the next set of notes, but this is an undamped oscillator, like an undamped second order system. And we'll break that down just to review that. But we're ending this set of notes with this, and then we'll jump right into the other. That it's a second order ODE. If we want to solve it, we need two initial conditions. And the initial conditions would be we can take the right-hand side of the equation to be 0 only because we're solving for... no, actually, so Shamik... Even if the equilibrium angle for the elevator is 0, you can still have perturbations of the elevator around 0. So it can still move like a little bit. So the reason that I'm ignoring this input is because first, I just want to analyze this as a homogeneous system. Like the elevator is the input to the system. And so for a dynamic system, you can just say, let's not apply any input right now. Let's just see what happens to the system purely based on changes in initial conditions or something like that. So the only reason I'm ignoring it is to look at the homogeneous part. There's no physical like justification for ignoring it as a general case. Great question. You are very welcome. So we need two initial conditions. So you would have the, like if you wanted to simulate this in MATLAB or whatever, You'll have an initial like perturbation angle at time 0, and you'll also have an initial, depending on how you divided, would your answer just be in different units? No, we definitely needed to divide through by that moment of inertia. That was a definite oversight on my part. Dakota saved the day. Okay. So, quick recap. We did the sum of moments. I know the Twitch saviors. We had a nonlinear equation. We solved for equilibrium. About equilibrium, you can solve for perturbation dynamics. And in the case where you consider the equilibrium where the elevator angle is 0, you get an equation that looks like this. So it's like a linear second order undamped thing. So I'm going to open up the next set of notes and we're going to break down this equation. Let's do it. Let's switch over. Okay. So this is our second set of notes. Like I said, right after class today, I'll upload the first set of notes. It'll look nice and clean. You can go through it. But definitely follow along in class. I think it's really a useful exercise. So, okay, this is where we left off at the end of the other set of notes. So let's just rewrite it. We have an equation that looks like this. Equals 0. And it's 0 just because I want to examine the homogeneous part of this equation. This coefficient k, it's all of that stuff, but for analysis, we're just looking at it as a constant. Okay. And you know what? We're even going to make this a little simpler. We're just going to say, why don't we work with familiar variables like x? What was the second initial condition again? So, because it's a second order system, you need an initial position and an initial velocity. So the two initial conditions were the position and velocity. Well, angular position and angular velocity for this rotating airfoil. So we have the second order equation. Let's just write it as x double dot plus kx equals 0. A real familiar equation. So we're going to do a little bit of review here. I know you guys took dynamic systems with different professors, whatever, but if we wanted to solve this equation, so see how this airfoil oscillates about the equilibrium, if we give it some initial conditions, here's a process that I like to use. All right. So the first step is you get the characteristic equation. And I'll just write this in terms of lambda. So I would have lambda squared plus k equals 0. I know you guys are all very comfortable with getting characteristic equations for linear systems at this point. Okay, so once you have the characteristic equation, the important thing from that is the roots, right? So this is second order. Okay, so there's going to be two roots. And you move the k over to the other side. You take the square root of minus k. And so you get imaginary roots. Plus or minus square root of k I. And, okay, perfect. And we'll just call this, we'll rename that variable omega naught I. Because that's just going to be the natural frequency in this case. So it's popular to view roots in the complex plane. So we have the imaginary axis, we have the real axis. So if we were to draw these in the complex plane, we would have 1 at positive omega naught. It's just living there on the imaginary axis, happy as can be. And we have the other one down here. All right. Do you guys remember the general solution for purely imaginary roots? Sine, cosine, yeah. So this is one way to write it. I mean, you could do it as a sine with a phase angle. I like to just break it into a sine and a cosine. And if you want to solve for these coefficients out in front, well, we'd have to utilize our initial conditions, right? So we have two initial conditions. You have an initial position. You have an initial velocity. Okay, so we're going to use those conditions. So I take my equation. I evaluate it at 0. That should be equal to my initial condition x naught. So that's going to be a1 cosine of 0 plus a2 sine of 0. And we know sine of 0 is 0. So that actually gives us a1 right away. Maybe we'll just fill it in down here. a1, because this term is 1. a1, that coefficient's just going to be equal to x naught. Okay, so to use the other condition, we need the velocity. So we have to differentiate x of t. So we're going to have negative a1 omega naught sine omega naught t plus a2 omega naught cosine omega naught t. And then we have to evaluate that at 0. So we're going to have negative a1 omega naught sine of 0, which goes to 0, a2 omega naught cosine of 0, and that cosine of 0 is 1, 0. Okay, so then we have a2 is going to be x naught, our initial velocity divided by omega naught. Okay, so we have a1 and a2, and now we can write our final solution. a1, which is x naught, times cosine omega naught t plus a2, so x naught dot over omega naught times sine omega naught t. So it's good to just refresh us on those steps. So why don't we look at the case where, I don't know, we have like 0 initial velocity and some initial angle displacement. So the point is, I don't know, I'm just gonna make up some frequency as well. I just want to drive the point home that this is going to be an undamped response. So the oscillations never die out. So we would call this like simple harmonic motion with no damping. So the benefit of linearizing a system is that once you get it into that linear form, we can quickly blast through and get like an analytical solution. And we know like, okay, this is undamped, complex, or just purely imaginary roots. It's a sine and cosine. This is what my airfoil is going to be doing. If I perturb it a little bit in the wind, it's just going to oscillate back and forth. Okay, but it turns out if we actually do that with a pinned airfoil, that's not what's going to happen. That is not what's going to happen. Okay, so a more realistic solution would be we have some damping in the system. For any physical system, you're going to have some kind of damping. Well, why did we have an undamped response for our airfoil? It comes back to our assumptions. I mean, probably the most basic that you probably already know. We assumed that the pin joint was frictionless. Well, no joint is purely frictionless. If the airfoil is rotating about it, there's going to be some friction in there. It's going to dissipate energy, and that would damp out the oscillations eventually. But the one that, the assumption that we're still going to leave it frictionless, but something important that we haven't considered is that the coefficient of lift depends not only on the angle of attack, but it depends on the rate of change of the angle of attack. So when we're doing our linearization, we have to consider that this coefficient of lift is not just a function of alpha, it's also a function of the rate. So, and the reason that is, like, is friction negligible when you try to fly a plane in this pattern in real life? Well, connecting this example to a real plane, we haven't made that full connection yet because you're not going to have this pin joint on a plane, right? It's not going to be fixed in space. So I wouldn't try to force this too much onto a plane yet. I think at this point in the course, we're using this example as more like an airfoil in a tunnel. Exactly. It's an airfoil in a tunnel. We're using this as a vehicle to explore some linearization techniques and show the connection between, you have some nonlinear system. How do you break it down to a linear system and then analyze it with some tools that we're familiar with? But we still want to enforce some physical understanding too. Like, okay, the best way I can explain why lift is a function of the rate of change as well. Let's make an airfoil, right? And let's put a pin joint. And depending on the orientation of this, we know that with a steeper angle of attack, you generate more lift, right? Okay, but imagine that, so that's just saying the lift changes with the angle of attack. But imagine that there's, wait, I didn't rotate this about the pin, did I? I just kind of rotated it arbitrarily. Not cool. Not cool. Let's change that. It's rotating about this pin. Okay. Now I'm happy with that. Okay, so let's say it's moving with some angular velocity, alpha dot. Well, what happens is we have some relative wind, right? And if you start rotating this airfoil, the relative wind that's felt at different points along the airfoil is different. Because we know that if this is moving with some angular velocity about this pin up here, this point down here is moving the fastest, right? Because it's farther away from the axis of rotation. So even if the air is all moving at some uniform speed, this is going to be feeling stronger relative wind because it's also like moving fastest in that direction. Does that make sense? So all that to say that the lift changes if an airfoil is moving just because the relative wind is kind of like a merry-go-round. Perfect. Because the relative wind is stronger at some points than others than if it was just statically at that position. And that's actually going to add some damping. Okay, so we're going to incorporate this assumption. So we'll still say the pin is frictionless, whatever. But now we're going to incorporate this effect into our model. So like I said, that'll add damping. So if we go back to the linearization step, we had some nonlinear equation. The right-hand side of the nonlinear equation, we just called it F. And when we linearized, oh no, we differentiated with respect to all of our perturbation variables. So we're going to add this now. Because now this F on the right hand side, it's going to be a function of alpha dot. So we have to incorporate that. And we're going to have a perturbation variable in alpha. Okay, this is our right hand side, and I'm writing this again because we're going to want to take this partial derivative. So I just want to have this here for reference. So the only thing that's going to change, like nothing, I'm just pulling the same function from before, but all I'm changing is that the lift is now a function of alpha dot. So it's a very small change. And then if we expand this lift, so all I'm doing here is taking this, I'm expanding it out in terms of the coefficient of lift. So we have 1/2 rho u infinity squared times the planeform area. And now we have the coefficient of lift. And, well, it's a function of alpha and alpha dot now. Okay. So our linear model, it now requires us to calculate this partial of f with respect to alpha dot. Well, okay, so if we want to differentiate this function with respect to alpha dot, the only term that's a function of alpha dot is this guy in here. Well, and it's multiplying the cosine, but... So we're going to get minus L2 1/2 rho u infinity squared times that planeform area. And then we're going to have the derivative of that coefficient of lift with respect to alpha dot. And then we just have to evaluate this at our equilibrium conditions. I even included the equilibrium angle of attack rate here, but that's just 0, because at equilibrium, the velocity is 0. So, okay, and then I have to multiply this by cosine evaluated at that equilibrium angle of attack. Okay, so all we did here, we took this function, we differentiated it with respect to alpha dot, and the only term that's a function of alpha dot is the coefficient of lift, so we just kind of generically have the partial of that with respect to that. So that's the derivative. And just to show some notation once again, whenever we have these partials, we're going to more and more lean towards writing them like I'm going to show you right now. So let's say it's evaluated at these points. We're just going to call that coefficient of lift, but it's partial with respect to alpha dot. And then you can say it's evaluated at those points. Okay. So, including this effect, we're going to get a new set of linearized equations. I want to give like a little bit of time if you haven't finished writing that quite yet. Maybe I can just zoom out here. But in this box, I'm going to put our new equation, which these two terms, like at the bottom, these are just from before. We're just going to have one new term that we just got from including the damping. Oh, here I remembered to divide by that. Imagine that. Okay. Okay, so I'm sorry. I know I'm jumping around here, but the term that I'm adding to this box is this right here. So I'm going to take that partial, multiply it by delta alpha dot. So when I'm writing this huge expression in here, that's all it is. So, okay. Well, this has a minus here, but I'm moving it over to the left-hand side so it becomes a positive. Okay, so I'm going to do 1/2 rho u infinity squared s. Okay, I'm not going to forget that L2. I'm just moving it over. And then for the coefficient of lift partials, I'm going to use that notation that I showed you. So coefficient of lift, but I put a subscript alpha dot to say it's a partial. And then I got to multiply that by the cosine up there. And then I need to divide by the moment of inertia about the pin. And then this is the constant that's going to multiply the perturbation in the angular velocity of the angle of attack. Whew. Are you guys doing all right? As I'm writing like all of these symbols, I'm like, holy cow. I think that's just one of the challenges with flight dynamics, that there's so many symbols and partial and subscripts flying around that it's like you get blasted in the face and you're like, what is even going on here? But like I said, the main goal here is a lot of symbols, but I think I get it. All right, cool. So we're gonna, speaking of symbols, we're just gonna try to make this a little bit easier to look at. So instead of these huge functions, we're gonna put in some constants. And even this moment coefficient on the right hand side divided by IP, I'm just gonna call that K2. And this equation is something we're, flying around. I didn't even realize I used that pun. Oh my goodness. I'm ashamed of myself for doing that. Okay. So let's analyze this system just like we did for the undamped as a little bit of review. We won't do it in quite as much detail, but we know that the characteristic equation for this, it's going to be lambda squared plus b lambda plus k equals 0. So now we have two roots, but they won't be purely imaginary. So like if we use the quadratic formula, these are our two roots. Okay, square root of b squared minus 4ac. All right. So you can get different kinds of roots out of this. But I want to look at the case where 4k is greater than b squared. So that means that this number under the square root, 4k is bigger, so this is going to be a negative number under the square root. And that means we're going to get imaginary numbers again. So you have complex conjugate roots. And whenever you have complex conjugate roots, we call that an underdamped system. Okay, so, all right, these are what our roots are going to be. So I can call this 1/2, and I can switch the order in here and throw an imaginary sign outside, or the imaginary variable. But from dynamic systems, we've defined some variables for underdamped systems. So why don't we use those? We know that the real part of the root is the negative of the damping ratio times the natural frequency, and then plus or minus the damped natural frequency times I. And just to remind you, the damped natural frequency is the natural frequency times the square root of 1 minus the damping ratio squared. So if you, we'll get into this like eventually, but because this like this k coefficient, this b coefficient, we know from earlier it represents all of those aerodynamic variables going on. Looking at a system like this, we know how those variables affect stuff like natural frequency, damping ratio, and so on. Zeta. That's right. I kind of, the way I write zeta, it changes from instance to instance. I don't really know anybody who has a solid zeta. That's a tricky one. Okay, so let's talk about the roots and Da Vinci maybe. Yeah, I know. He'd probably have a beautiful way of writing zeta. If you can see from the roots, if b is 0, then we would end up with purely imaginary roots. But as we increase beta, these two roots kind of move around like this. So that's increasing beta. Or b. Why am I calling it beta? It's just a b. And if you increase b enough, not to bring back nightmares of the root locus, right? I know people don't tend to like root locus, but these roots would break into the real axis, and then like one would move this way and one would move the other way. So you can get some different types of second order behavior. But when it's underdamped, it's going to be in this zone out here somewhere. Do you remember the general homogeneous solution for an underdamped system? Let's write it here. The difference is you have a decaying exponential out in front. Oh, I need a coefficient here. Cosine of your damped natural frequency, sine of your damped natural frequency. So now we're still going to have a sinusoid, but I'm going to draw the envelope here. I'm going to do my best. Okay. Something like that. We're going to try to make this symmetrical. Whoa. That's beautiful. That is fantastic. All right. Let's just throw this in here. Just a perfect sinusoid. Okay. So in this case with the damping, you have decaying oscillations. Is it possible to learn this power with extensive training? Extensive training and meditation and performance enhancing drugs. Okay. So, okay, we've done this linearization. We added damping, and we looked at the typical types of solutions. So let's get to the main takeaway here. It may lead to abilities some would consider unnatural. Thank you, Palpatine. Apparently, you can also solve for A1 and A2. You can. You can also solve for A1 and A2 in this case. Although we won't go through all the details here. Thank you for that, though. Okay, so the main takeaway. If we consider the dynamics of a system, so in our case it was it is known. We had our pinned airfoil in the small neighborhood of an equilibrium point. So the dynamics in the small neighborhood are called the perturbation dynamics. The resulting equations are linear. And the nice thing about these linear systems is just in like a couple minutes, we have, these have clean analytical solutions. Have you heard the tragedy of Darth Estes? Okay, linear, okay. These have clean analytical solutions. Yes, the tragedy. Oh, that is so good. All right, so, but even though these equations are simplified, I want to drive home that they're still useful in real life situations, even with aircraft dynamics. I mean, we're doing it for a reason. They're useful in real life situations where a system operates close to some nominal state. So think about when you're on a commercial aircraft. You're mostly flying at a steady condition where it's like a constant velocity. It's not rolling all over the place and pitching. It's at in equilibrium. And so the dynamics of that aircraft about that nominal flight condition, they're described really well with a linear system. So an aircraft operating at a nominal flight condition, which is most of the time. Okay. Those are my main takeaways from this first part. Don't get stuck in the weeds too much. If you walk away with these points, you're doing pretty good. All right, we have a couple minutes left. And I want to talk about state space. Now, state space, when we do it in dynamic systems, we limit our discussion to linear systems. So in 340, you work with LTI ODEs, linear time invariant ordinary differential equations. All right, state space applies to nonlinear systems as well. So I want to show you that because you need that for the homework as well. So state space, just to review, it's especially useful for numerical simulations or like any of our aircraft or any dynamic system. It's the standard mathematical representation that we use for numerical simulation. Why is that? Because numerical integration techniques are all pretty much based on first order systems. Like think about the Euler forward method. That's a first order approximation that uses the slope. So it's useful for numerical integration. And we also have like other nice modes of analysis. You can talk about eigenvalues, eigenvectors, and those are computationally effective ways to characterize dynamic systems. So here's the main thing that I want you to take away. State space is not limited to linear systems. It's the standard for simulating nonlinear systems as well. So we're going to show you state space for nonlinear systems, and it's really not difficult. So don't worry. You're going to be just fine. Okay, so for an nth order system, we've been working with second order up to this point, but a general nth order, you're going to define in states. So we'll just call them X. X1, X2, all the way up to Xn. Doesn't really matter the variable name you use, but X is pretty typical, Z is pretty typical. All right, you're going to have M system inputs, and we're going to name those. U is the most common variable for inputs. So we're going to go all the way up to M. And then if you have P, system outputs, and when we're talking about system outputs, these are sensor measurements usually. In real life, you rarely have access to the states themselves. You get measurements from sensors, and then from there you estimate what the states might be. But just think of outputs as it's information you're getting off of sensors, and won't M and N be the same? No, they don't have to be the same. Because like just the pinned airfoil, for example, we had 2 states, so N was equal to 2, but our one input to the system was the elevator angle. So that system has 2 states, 1 input. So N and M can be different, certainly. Okay, so the P system outputs, we're going to call them Y. All the way up to YP. Okay, so if you define states, inputs, and outputs, here is state space form. What I want you to notice, this is first order. State space is by definition first order. So you're only going to see 1 dot on top of all of these. So our first state, x1 dot, is some function. So if you model this at fine physical resolution, your N would go up. Yes, that is the case. So x1 dot is a function of time, my N states, and my M inputs. And this function could be nonlinear. Let's fill in some more of these. X2 is generally a different function of the same stuff. Maybe different combinations of it. We're going to do a couple examples, but it looks like the examples are going to bleed into Friday. Okay, T, X1, up to Xn. Okay, so all of these first order x1 dot, x2 dot, xn dot, those are our state equations. They're first order. Now our output equations, those could also be nonlinear functions of the states and the inputs. And let's just do like one example of that. So this function, we're just calling it H. X1, all the states, great. So you don't see here any like A, B, C, D matrices. So you can only formulate those matrices if the system is linear. But even if you can't make those matrices, it doesn't mean you can't get a state space equation. Let's see if the example is next. Okay, we're going to get to the example on Friday, I think. But you can collect these equations in a vector form. So you'll have your standard state vector, x1, x2, all the way to xn. Your input vector, u1, u2, up to um. Our output vector, y1, y2. We said there could be p outputs. So if I take the one derivative of my state vector, I'm going to have x1 dot, x2 dot, all the way to xn dot. And this is going to be, remember we said x1 dot was just some f1, some function. But here I'm just going to truncate the notation a little bit. You could say it's a function of my states, but you could just put the state vector. Sorry, I went up there. I didn't mean to. My input vector and time. And, this would be f2 of my states, my input vector and time. And you go all the way down. I think you get the point here. And you can write this even more compactly as a vector function f of t, my states, and my inputs. So if you just want to concisely consolidate your state equations with this kind of notation, this is the way to do it. So I'll do this with the output, and then because we're right at 420, we'll finish here. Because, it looks like, we'll wrap this up Friday. And we'll do a couple examples, so it'll be perfect. Okay. So we'll have y1, y2, all the way up to yp. So this will be some general function, could be nonlinear, of time, my states, my input. My second output is a different function of those same things all the way to the end. And so we can call this a vector function h of t, my states, and my inputs. All right, and so Friday we're going to do examples. We're going to do examples. Thank you guys for your attention. Thanks for your participation. I appreciate you guys. We're just getting started. We're going to get into a groove. We're going to get on the same wavelength. Thank you, UBMAE student. I appreciate it. We'll get into a rhythm. Jordy says, hell yeah! Yeah, thank you guys. Lecture got intense again as the beat dropped. That's right. Guys, don't forget, we do have office hours. Our TA, Saeed, has office hours tonight on our Discord. We're reviewing 340. It's good to see that stuff again, just refresh it. So Saeed's going to be doing office hours tonight. I'm going to be doing office hours tomorrow night. And so I think we basically switch off every night, except Tuesdays. We don't have office hours Tuesday. So definitely go to Discord, get help with the homework. And like I said, Friday we'll, office hours are the spot. Yeah. We'll do examples Friday, that'll help too. Why again as in go up with increasing resolution. So I think the idea there is, in real life, systems are infinite dimensional. Like a good example is, so in 334 lab, we model a flexible beam. Actually, did we even do that last year? Last spring was weird, with COVID and everything. But we have a flexible beam that we model, and you can model it really well with a second order system. But it doesn't capture all of the possible movements that this flexible beam can make. If you do a fourth order model, it's even better. And, if you make the model 10th order, 12th order, you could theoretically go all the way up to an infinite order state space system to describe it. But we find in real life, that's overkill. Like that flexible beam, second order model describes most of its behavior. Fourth order, maybe you need that for a little more detail. But basically, if in is going up, if your model's order is going up, you're capturing more degrees of freedom. Wouldn't the xn represent physical positions that the part can occupy within the model bounds? You got to be careful with states. Okay, well, so like for a physical system, often we're talking about position and velocity for states. So I guess you're right that if you think of a general flexible body as a bunch of rigid bodies connected together with like springs and dampers, you could have states be the position and velocity of each like node. So that's like happening in finite element models and stuff. But states don't always have to be physical. Like when we do experiments to model something, there are algorithms that'll return a state space model. But most of the time in that case, the states aren't positions and velocities. They're just, how would you describe it? It's kind of like a curve fitting technique where it's just trying to find a model that describes the data, and it doesn't care physically what it means. So that's the topic of like system identification. It's more like a curve fitting thing where the states might not come out having a lot of physical meaning. An approximated state condition within space and time. Well, so like fundamentally a state is the minimum set of knowledge you need about a system to predict its dynamics for the next step. Like if you know the position and velocity of a particle, that gives you some ability to predict where it'll be a short time from now. So I think of a state as just like the minimum amount of information you need to characterize the dynamics of a system at any given time. I have to run to vehicle dynamics office hours in another minute or so. So I'm going to leave you guys with some tunes. Thanks once again, guys.